I know half the people in the world don't even have electricity. And what, 6% have a PC, so it's somewhere in between. It's probably closer to 10 than 50 for sure. Communication is related to democracy. It's related to the development of infrastructure and jobs that generally aren't available in large portions of Africa, South America, and Asia in particular. So we've got a long way to go before we have to worry about it, but certainly the point's well taken. Then you would start worried about specifically energy consumption in use and getting them to last as long as possible. That's a good point. Other questions or comments?
Why do we always assume that in the developing countries that they want something less than what we have?
They don't want anything less than we have. I don't think anybody's assuming that. I've never seen anybody admit that. I mean, maybe implicitly, right? But you can't just snap your fingers and say, well, Africa's going to have the same standard of living as America, as we know, right? I mean, it's being realistic that development happens over time. And that development needs to leapfrog a lot of stages. Actually, I'm going to come back to this point, especially when we talk about energy, because what we're going to see is a lot of the energy in the future is going to be consumed by the developing countries, not the developed countries. And that's really going to change the dynamic tremendously. And if they go through the same polluting path and the same length of time, they'll probably be a lot unhappier if it takes them 200 years to reach the same level of development that we're at. Especially with television and radio, and people know how other people are living, it's probably not sustainable. So this leapfrogging concept is critical, right? And I think people are aware of it, but they're also realistic too in that these things happen in steps. But it's a good point.
You can also think about the fact that there are a very small number of consumers in the United States who would love to have a recycled phone to save money or because it's recycled. That
too, actually. It is a niche market, and
right.
it's observed more in Germany, actually, than the United States. But there is demand.
Right. So if there's demand in a developed country, then there can be demand in an undeveloped country. And they're not getting less than what those consumers want.
In that sense. And if you can make the phone look cool, and that was the whole point of the MHP here, because certainly the, and this isn't the stylistically most attractive phone. We can certainly work on it. But certainly the concept that you could take the guts of beat-up phones and make them look brand new and deliver them at a low cost would have this appeal, right? And they might not even know the difference, right? A lot of laser toner cartridges, the phones that you buy, the disposable phones that you buy are 87% recycled, right? And we're not sensing that that's somehow something less or that we're getting something inferior. Right, so it's, the packaging, how you deliver it, makes a big difference.
Just as a comment on what she was saying, I mean, what he implied was that these phones were cheaper, and so it would make sense for them to buy them because they're more economical. Not that they necessarily wanted less, but as an observation of my own, I vacationed in Uganda last year, and I was shocked that there was at least 3 cell phones a house amongst the people that I met, and I guess everybody in the whole country wouldn't have them, but a lot of people I met were students at Makerere University or people that were in government and stuff like that. So of course they had them, but they were extremely popular. And even though their electricity wasn't stable because it went out a lot, which I'm sure is common in a whole lot of countries, you do need electricity to run the system. But they didn't really have landlines, but they had cell phones because it was easier because of the air. You don't have to put the infrastructure in for the wires,
Yeah.
So
you can deploy these systems a lot faster.
Right.
And that's another reason to sort of encourage the diffusion. There are waiting lists in some countries like Uganda in that region of the world where there are waiting lists 10, 12 years to get a landline, right? Whereas if you could deploy a few base stations, you can even remanufacture some base stations. You can really set these systems up quickly and again, accelerate the development. Right, and that's happened. That's a story in a lot of places, for sure. And we'll talk more about this later in the term. We'll go through examples of eco-design, sustainability, and this will come up front and center. Other comments? And that's actually a really nice segue because we should look at some global statistics about where energy is consumed. And right now, it's in the industrialized world, for sure. Here's the industrialized world. Here's Eastern Europe and the former Soviet Union. Look at, this is up until 1997. These are actual numbers and then projections, right? By 2020, it's predicted that more energy will be consumed in developing countries than in the currently industrialized countries. So the form of that energy and how it's being used, and I guess I should say the efficiency of the energy, not just the form, but the efficiency and how it's being used, are critical for us to consider in this development. This is a quadrillion BTU. So this is 10 to the 18th joules. Okay, it's a lot of energy. Okay, now these are stats you can't see from where you're sitting, but this is world energy use efficiency. Okay, the United States has about 260 million people, 1997 numbers. If we look at energy use per person, that's about 335 megabTUs per capita per year. Okay, which is among the highest energy consumption per person in the world. We do use the most energy as a nation in the world. If we compare it to Canada and Russia and Japan, we use far more energy in this country. Per person, yes. It's colder.
Yeah.
Quite simple. So these numbers are you can start playing around. If you go by per person, or you go by per GDP, you can say, well, Russia is colder too. What's going on there? Per GDP, it's a lot higher, right? But the fact is, the GDP in Russia is a lot lower, so fewer people are contributing to the economic development there. So your mind can bend a little bit. And yes, there's a funny little book called How to Lie with Statistics. Right? So, you can play around with the numbers and say, well, per person, the United States doesn't actually consume the most energy. Canada does, right? Or, but how many people live in Canada, right? And, what's going on here? I mean, if you look at the actual impact, we're looking at 11.7 quadrillion BTU versus 88. I mean, it's a factor of 8 higher, right? So, can't blame that one on the Canadians, but... you can have more fun with numbers. This is where that energy comes from. So we're looking at just basic energy. Most of it comes from oil. Here's world statistics. Petroleum, about 40% of the energy. About 25% is coal. About 21.5% is natural gas. Nuclear is about 6%. Hydro is about 7%. And the U.S. numbers are not far from there. Okay. A little bit more nuclear, a little bit less coal, but roughly the same proportion. Again, if we go back, actually, 88 quads of energy used in the U.S. versus 380 in the world. Okay, so that's almost 20%, roughly. A little bit more than 20% of the energy we use here in the United States. So it shouldn't be a surprise that our pie is very similar to the world pie, because we're driving about 1/5 of that. Okay, electricity consumption. So moving away from just energy and now talking about electricity, special form of energy. Most of that comes from fossil fuels. Look at the USA here. About 56% comes from coal, about 21% from nuclear, 22% from nuclear, about 10% from hydro, 11% from hydro, and about 9% from natural gas. Okay, so you get a sense of the distribution. Here's a coal-fired power plant. For those of you who haven't seen one before, what are these things here? Cooling towers. And what's this? Smokestacks. What's the difference between a cooling tower and a smokestack?
Steam and pollution.
All right. Yeah. So this is basic steam, exactly, and this is pollution, if you will. Right. But there's a lot of stuff going on down here that are trying to clean it up before it gets up there. All right. And we'll talk about that. Okay. Electricity consumption in the U.S. That's a straight line, pretty much, right? Going up. I'll break it down here in the U.S. These are 1998 numbers. Good fraction, and we just saw this pie graph. About 2,000 billion kilowatt hours of coal energy production here in the U.S. Okay, if we take that line across, right? And there was a question.
So coal-fired plants have the same cooling towers that a lab would have. These chemically nuclear.
The design of the cooling tower would be very similar. Yes.
I automatically assume that was nuclear whenever I see that.
Yeah, most people do. That's why I brought it up.
Wow.
That's exactly why I brought it up. Yeah, but you need cooling towers for both. Absolutely. But the smokestack doesn't exist in the nuclear. And thank goodness for that, right? Okay. Now, some disbelief was expressed earlier in the semester, and I remember that we could be using so much coal. So I just threw this example in. Here's a typical 500 megawatt power plant, probably similar to the one that we showed here, burning coal rated at 28 kilojoules per kilogram. So that's the heating value. It's how much energy you get for a kilogram of it. These plants will not always run at 100% capacity. This would be one that has an average annual capacity of 65%. So there's some maintenance. They don't always run at peak. Okay. Now, if you look at how much power is produced by this plant in a year, so a megawatt's a unit per time. So if I take megawatt hours, that's a unit of energy, right? So joules per second. Okay, so this is just an expression of energy, 2.8 times 10 to the 6 megawatt hours per year. This would be about 1/1000th of the U.S. proportion that comes from coal. It's about right. Okay, typical power plant. How much coal is that? It's 1 billion kilograms of coal. I mean, you think about it, it's these huge numbers. How much ash produced? That would be about 1 times 10 to the 8th, so that's 100 million kilograms of ash, about 15 million kilograms of sulfur, and 2.4 billion kilograms of CO2. One power plant. Well, this is about 1/1000th of the U.S. proportion that comes from coal. Okay, not all coal is the same, but this is typical numbers. Okay.
Where's all this coal coming from?
The ground. There's a lot under there, right? Earth's been around for a long time.
Yeah.
Organic matter's been around for a long time. We have a lot of coal left. By current usage rates, we got about 200 years left of coal at the rate that we're going, even with growth, right? Would we want to burn all that coal and stick the CO2 into the atmosphere, you know, at 2.5 billion kilograms of CO2 per year? So these are real numbers. I promised that later in the term we'd give the real numbers. Here they are. Okay.
Are the plants usually closer to the coal? Like
Stick it on a train. You ever get stuck on a, you know, you're waiting for a freight train and you see like one after the next after the next? Yeah. Yeah, actually, can you see, if I go back here, I guess all right, there's going to be a coal like pile just way down in the corner here, but here's like the chute, right? I mean, you just keep feeding it. Keep feeding it in. Question?
Is coal distributed evenly on land, or I mean, is it?
No, there are places like coal mines, right?
Right.
There are places that have richer coal deposits than others. But yeah, there is a lot of it around everywhere. But yeah, certain places have a better, richer deposit than others.
Where does the huge ash goes? Ash?
The ash, where's the ash go?
Yeah, okay, great question. So let me answer. Okay, so here's your coal pile. So this is what a typical coal-fired power plant would be. Crush the coal, burn it, use the heat to generate steam. The steam turns the turbines. Okay, and what happens to the steam? Well, you're going to condense it back down, cool it down a little bit, because otherwise the process would get out of control here. So there's your cooling tower. Pump that condensate back into the boiler. Okay, so that's going to become steam again. And yes, the million-dollar question, actually the $200 million question, is what happens to the pollution, including the ash. Well, we've got this electrostatic precipitator that's going to deal with a good amount of the particulate matter that comes from the combustion process. So basically what an electrostatic precipitator does is it charges the particles, and then there's a bunch of plates in there. And basically the particles drift toward the plates and stick to the plates, and then you knock the plates and then collect them down, and you basically have this big pile of ash at the end of the day that you have to somehow treat. Okay? That would be landfilled. It depends what's in it. It could be hazardous. It has to be treated before you actually landfill that material. But ash is not the only concern. There are other concerns. Sulfur. You can have up to 6% sulfur in coal. Sulfur is going to produce sulfur dioxide. We'll talk more about that in a minute. So we've got this scrubber here that basically puts limestone in to basically pull the sulfur out as calcium sulfide, right? And that's shown down here. And you've got to manage all this, right? And it's not very economical to use this for anything. Okay, and this is all before the stack releases it. So you treat it for NOx, you treat it for particles, you treat it for sulfur dioxide. All right. Question?
Why do you reheat before putting it in the stack? What's the reheat at the end?
The reheat, which line you pointed
Right
to?
above the
Next to
scrubber.
stack.
Oh,
That's for the incoming air.
it'll, yeah, no, here I think it's at this point. The reheater will actually make it a bit more buoyant. Dilution's a solution of pollution. You don't want to push it out, right? So to help bring it up. Good point.
One thing that was instilled in my head when I was working at Shell was every time you had a flow process, I mean, you have all the elements in there, but for the smokestack and the cooling towers, they always put dollar signs as it comes out.
Yeah, this is just dollar signs, exactly. You know, it's interesting. About 40% of the cost of a power plant goes to environmental controls. We talked about that 2.6% of GDP. I mean, that's just a ton of money right here, and we're all using electricity. I think it was about 80% in Michigan of the energy, 60 to 80. I don't remember. I thought it was closer to 80. In Michigan was coal. About 5% of the energy that's produced at the plant goes to like the electrostatic precipitator. Right? So that's just strict waste right there. And only about a third of the transmission reaches the customer. So 2/3 of the energy produced is waste in the transmission. Okay. So I mean, this just gets you some perspective on the magnitude of what's going on here. Yeah, it is massive. Okay, and there are lots of environmental issues. I think we're familiar with them, so we'll go through pretty quick. Carbon monoxide, particulate, hydrocarbons, sulfur dioxide, NOx, carbon dioxide, and mercury. Here is the percentage produced by stationary sources versus mobile sources. At the top, mobile sources. Right below is a stationary source. Now, if we add it all up, about 65% of carbon monoxide pollution in the U.S. comes from stationary sources. Just over half of the NOx comes from stationary sources, and a whopping 90% of the sulfur comes from stationary sources. Gasoline doesn't have much sulfur in it. Okay, most of the sulfur comes from the production of gasoline, not from the burning of gasoline, and those are stationary sources also. The particulate, about half, comes from stationary sources.
Plants? What are you referring to?
I don't think I did say mobile plants.
Pollution generated by mobile
sources of cars, trains, planes.
I'm sorry. Okay.
Mobile sources. Okay, here's just another view of the same story here. This is a coal-fired power plant. How much gram per kilowatt hour is produced? So basically a kilogram of CO2 per kilowatt hour, right? And we were in the billions of megawatt hours, right? Okay, so it gets you a sense of how much CO2 is coming out. A few orders of magnitude less for sulfur, but still just a tremendous amount, right? And these numbers could come in handy. I just more put them here for reference than anything else. Where does carbon monoxide come from? Why are we worried about it?
Is it incomplete?
Incomplete combustion, right? And it says it here. And so, from a technical standpoint, if you're not burning your fuel completely, not oxidizing it completely, right? Remember what burning is, right? I combine it, carbon with oxygen, basically, and that produces a lot of heat in the formation of CO2. But if that doesn't occur completely, you'll be left with CO, carbon monoxide. So there's a lot of technical ways, right? If you don't have enough oxygen in there, it won't burn enough. If the temperature isn't high enough, it won't burn enough. If you're sending the air through too quickly, it won't burn enough. And if you've got turbulence, then you don't have a complete mixing of the air, it won't burn enough. Right? So the point is incomplete combustion, carbon monoxide. Right? Cold starts in your car, carbon monoxide, you know about that. Okay, and the health reason here, of course, hemoglobin in blood has a higher affinity for carbon monoxide than it does for oxygen. So it starves you of oxygen. Particulates, and we went through this very briefly earlier in the term. Big particles settle out. Small particles, especially way below 1 micron, you might breathe them, but they might just pass right back out. Okay, so there's a size range we're mostly concerned about, and that's between 0.5 micron and 10 microns. Okay, so we had different standards. Particulate matter less than 10 micron, particulate matter less than 2.5 micron. And particles are of concern. When you've got particulates in the atmosphere, particularly in conjunction with sulfur oxides. So this combination is particularly hazardous to human health, okay? And they've been linked to lots of hospital visits from respiratory infections, cardiac disorders, bronchitis, etc. Okay. And this just shows, you know, the human respiratory system. The nasal passages can clear out stuff bigger than 10 microns, and there isn't much of it anyway, again, because it settles. Below 1 micron, it passes through. Different types of particulate, right? Aerosols, pretty much any type of ground particle. Could be solid, could be liquid. Dust is a particular form where it's a solid that's kind of ground down. Right? We all know dust from the house. Smoke is unless it's from a coal-fired power plant, that's ash. And soot is more tarry. That basically comes from diesel. Okay, and mist is a liquid. Okay, so different types of particulate matter we might be concerned about. For cutting fluids, we're concerned about mist. For power plants, we're concerned about fly ash. For smoking, of course, it's smoke and fire. Soot comes from diesel. Right. Here is, and we mentioned this before, from particulate matter less than 10 micron was the old standard. Now we look at both particulate matter less than 10 micron and 2.5. EPA claims that bringing the standard, or establishing a standard for PM 2.5 has saved 15,000 lives per year. There are ways statistically you can come to numbers like this. But of course that cause and effect is very hard to establish. Most particulate matter comes from fugitive sources, piles of stuff. From industrial processes, could be dirt roads also, of course, where people drive. Fugitive sources could even include the soles of your shoes, or particulate matter, and things wear down. But most of this comes from fire and wind-driven soil erosion, construction, and mining. Okay. Soot is, most people think of diesels as being extremely unhealthy. And the reason, and we've talked about this before, these particles have very large surface area. And soot tends to be particularly sticky when it comes to adsorbing constituents on its surface. So high surface area, sticky surface area, and, oh, by the way, it's in the presence of things like sulfur, sulfur dioxide, right, and other metals that can be found, and they're listed here like cadmium and chromium. Right? So you basically got this soot particle that's can be a delivery mechanism for things that you'd otherwise exhale. For instance, sulfur dioxide, we talked about that. It's very toxic, right? But if you just breathe sulfur dioxide, now you want to, right? But very little would get deep into the lungs. It's when the sulfur dioxide attaches to a particle and that particle sticks in your lungs, then you got a real problem. Right? So these particles are not only hazardous in and of themselves, but they're a vehicle for other things to get into your lungs. Oh, this is just a description of Stokes' law here. A small particle of 1 micron will take 290 days to settle out of the atmosphere. So 1 kilometer elevation there. So settling is only a minor mechanism of cleaning particles out of the air. Right? Rain does a much better job. So a lot of the fallout comes from precipitation. And impaction, too. If you've got some circulation near the surface of the Earth, then the particles can hit the ground and then fall out. Sulfur, we mentioned, most of this is from power plants. Only about 3% comes from highway vehicles. Besides power plants, we've got sulfur emissions. We talked about copper smelting, petroleum refining. We saw some numbers on that earlier. And cement manufacture, which we haven't talked about, is important, too. A lot of energy, a lot of sulfur. Roughly half of sulfur in coal is really easy to get out if you just wash it. The other half is chemically bound, and there's not much you can do to get rid of it besides burn it and then handle that sulfur afterwards. Okay. Natural gas also has a lot of sulfur, but it turns out you can get rid of that sulfur. In fact, they put in a little bit of the sulfur smell back in so you know that you have a natural gas leak. If you've ever had a natural gas leak or been around one, you know it smells bad. They put some of that sulfur back in. But it can be effectively removed very easily. Okay, so what's the deal with sulfur dioxide? Well, you know not only is it toxic in and of itself, but it's a major constituent of acid rain. Now, one of the things to note here is that sulfur dioxide is very stable. That is the product from combustion, sulfur dioxide. So if it's stable, you might wonder how it becomes sulfuric acid and sulfate particles in the atmosphere. Well, the deal here is that there are other things in the atmosphere that can catalyze the transition or the transformation of sulfur dioxide to sulfur trioxide. And that's generally associated with pollution and the photochemical energy that's in the sky, essentially. So you got various catalysts that can, such as metal oxides, such as NOx, in the presence of sunlight, can catalyze the reaction of sulfur dioxide to sulfur trioxide. Now, that's less stable and is likely to become sulfuric acid and particles than sulfate aerosol particles. But that takes place over time. The point here is there's a series of reactions that lead from SO2 to H2SO4, sulfuric acid, sulfate particles. Okay? And that takes time, right? So if I have a big smokestack, this one's over 800 foot tall, okay? There's time as you're spreading that pollution out for that reaction to actually happen, okay? Right? Stick the stack way up high, and that sulfur dioxide is going to be up in the sky for a long time. It's not going to make contact with the ground in a dry deposition, right, to fall out. So here's a basic description. The longer it's in the sky, the higher the percentage it comes out as acid rain. Okay, but if you got a short stack, basically over the first day and the second day, most of the deposition would be dry. But that, again, over time becomes acid rain. Okay, so the smokestacks from the coal-fired power plants in England create a problem for lakes in Sweden. This is one you've already seen. This is near a copper smelter, right? This is sulfur dioxide damage, right, from impact. So sulfur dioxide is very toxic. Acid rain is also toxic. And I should have shown some of the forests in Germany, in even North Carolina, where acid rain damage has done. But I don't have a picture of that here. But acid rain is very damaging, too, especially out in the Smokies. Anybody been to the Smokies before? Just one person. But you see a lot of that forest there is not very healthy. And the reason for this is you'll get these layers of fog that have acid essentially in the fogs. It's like an acid fog instead of an acid rain. So the trees are just sitting there and they don't have much of a chance. So a good part of the forests are actually dying there. And there are zones around it where they try to control the sulfur emissions. Okay, so if we summarize the environmental impact of sulfur dioxide, we can put it into 4 categories. It's toxic to humans. It's acid, can acidify lakes and surface waters, damages trees, and also buildings. Okay. One thing to note here, did anybody hear of this London fog episode in the 50s where 4,000 people died in London? We're going to talk about inversions later in the term when we talk about smog. Oh, no, I think we're going to talk about it next week, right? Think about it. Yeah, we're going to talk about transport of air pollutants. And one time, we say dilution is a pollution solution to pollution. If you have a temperature inversion, such as that might occur over Los Angeles in the summertime, and the air can't move, right? Then you're pretty much stuck with the pollution that you emit. And what happened in the 50s were that the smokestacks weren't very tall, and they were below an inversion. Okay, you can have winter inversions and summer inversions. And so what was going on is there was a lot of soot, a lot of particles, and a lot of sulfur dioxide. And people were breathing this, and it basically lasted 4 or 5 days. Right? Basically, they say day was night for those 4 days. And yeah, a lot of people died. So there's showing that the synergistic combination of sulfur oxides and particulate. They say that sulfur dioxide contributes to a number of premature deaths. And again, I don't know where they get the numbers from, statistics, of course, but it's very toxic. Here's the acidification of natural bodies of water. Natural rainfall should have a pH of 5.6, right? Some of you might have guessed 7, right? Why does natural water have a pH of 5.6? Clean water. Anybody know? Anybody taken an environmental chemistry class? If you were to go down to my lab, we have a water purification unit. And if you just take water directly out, I mean, this is semiconductor grade pure water. You take the pH, it's 5.6. It's not dissolved oxygen, but that's getting to the point. Say again? Well, carbon dioxide, actually, not oxygen. So what happens is you got carbon dioxide in the atmosphere, and that carbon dioxide then starts a chain reaction inside the water that releases protons, that acidifies the water slightly. So the carbon dioxide becomes carbonate and bicarbonate, and there's some equilibrium reactions that result in the release of acids. And at the equilibrium point, with the amount of carbon dioxide that's in the atmosphere, you'll get a pH of about 5.6. Right? Aren't you glad you're not doing that homework problem? We used to assign it. It's actually not that hard. You have to remember some Chem 101 stuff, though. So here's the point. Acid rain, you see the contours of iso-pH, if you will, and some real hot zone here, where the west, basically, the wind drifting up here, depositing in some lakes that don't have natural buffering. So if your lake has natural buffering, for instance, if it has a bed of limestone, it will be somewhat protected. A buffer is something that resists changes in pH. So a limestone bed lake will have a natural buffer to pH drops. But out here in New York, I believe the base is granite, which doesn't have any buffering capability. So you see very acidified, a pH of 4. Right? Some rain can come down with a pH of below 3. I mean, that's like citric acids in that range. I mean, it's pretty bad. Okay, 2/3 of coal consumption occurs east of the Mississippi River, so I guess this shouldn't be too much of a surprise. Here, just shaded in yellow, are some places that are naturally susceptible to acidification changes in surface water. And here's just some stories here from Sweden. Lakes before 1935, almost all the lakes above a pH of 6, and now a good fraction of them below. Actually, these are 1971 numbers, sorry. But you see the shift in the pH. Same with the Adirondacks in New York. So just telling the same thing. It causes damage to trees. Basically, these are 1983, 84, 85, 86. These are numbers you can't read, but for European numbers from the United Kingdom, at the time West Germany, Switzerland, Netherlands, Luxembourg. And basically showing that over time, the health of the trees and the needle droppage was actually growing. The health was decreasing. And it was well correlated with sulfur oxides and nitric oxides leading to acid rain. Okay? And we should note, too, that buildings are affected by acid rain, too. Limestone, marble in particular. A lot of statues being replaced. In Greece here, the outdoor statuary, the actual statues outside being replaced. The building itself up on the Acropolis being replaced with acid rain resistant materials, things like gypsum and plaster. Replicas, essentially, because the actual marble and limestone cannot handle the acid rain. The Field Museum in Chicago had to undergo, a few years back, a major renovation due to acidification of the building itself. Okay? And it's a natural thing to happen. Actually, marble and limestone are chemically the same, calcium carbonate. In the presence of sulfuric acid, basically you get a soluble calcium sulfate. Right? And as we talked about last time, these are salts. Salts are completely dissolved in the solvent, and so you've got basically your calcium base washing away. I think here's the erosion of St. Paul's Cathedral, right down there in the Vatican City, 200 micron per year loss, just erosion of the building due to acidification. Okay. We should add carbon to our list. These are more statistics. If we look at carbon emissions per capita, the United States wins hands down. Our carbon emissions represent over 20% of carbon emissions in the world. Okay. And here's Canada. It's roughly 1/14 of carbon emissions relative to us. Per capita, though, they're pretty high, but still, we're a lot higher. A lot of carbon release. Okay. Here is a basic problem, because, again, there was some disbelief expressed about how much carbon dioxide is released. Let's look at carbon releases from coal versus natural gas, or methane. Okay. So this is just a problem looking at the emission of carbon dioxide from coal, assuming that coal is about 67% carbon by weight. Okay, and it has a certain energy content, 28.4 megajoules per kilogram. If we assume that natural gas contains 74% carbon by weight and has a higher energy content density, 54 megajoules per kilogram, what's the relative carbon ratio for the delivery of a kilojoule of energy from coal versus a kilojoule of energy from natural gas? Which one releases more carbon dioxide? And you can go through the calculations. It's not a hard thing to do. Carbon combines with oxygen in the combustion process to form carbon dioxide. Molecular weight of carbon is 12. 1 mole of carbon becomes 1 mole of carbon dioxide, which means 12 grams of carbon has a molecular weight of 12, becomes 44 grams of carbon dioxide. Carbon is 12, oxygen is 16. 16 times 2 plus 12, 44. Okay, so 44 grams of carbon dioxide upon combustion. Okay, so we can just go through. Here's 67%. This is the percentage of carbon in the coal. We get 44 kilograms of carbon dioxide for every 12 kilograms of carbon that's burned. And we find that there's 2.4 kilograms of carbon dioxide per kilogram of coal burned. And if we convert that to energy, that's 8.6 times 10 to the minus 2, so 0.08 kilograms, or about 80 grams of carbon dioxide per megajoule. Okay, and we could go through the same calculation for natural gas. And what we see that the carbon dioxide release, providing energy from natural gas, releases less carbon dioxide than coal, almost half. Okay? So here's another point, is where you get your energy matters. In the sense of global warming, natural gas is cleaner, okay, from a CO2 perspective. Okay. And we know why this is important. Carbon dioxide concentrations in the atmosphere are growing. We've measured that, and there are some scenarios here that are almost frightening to look at. We had a 270 parts per million carbon dioxide concentration in the atmosphere before the Industrial Revolution. Here are 3 scenarios that the Intergovernmental Panel on Climate Change, this was a group of scientists convened by the United Nations, scenarios also looked at by our National Academy of Sciences. Here's a business as usual, up to 1,200. This is a 4 times CO2 world by 2050. Here's another scenario that takes a little bit longer to get to the same place. Here's a scenario where we actually do something. And still, the carbon dioxide is going to go up, even when we do something. Okay, and we know why this is important. We talked about the absorption bands. We have a lot more to say about global warming in a couple of weeks, okay, and some of the predictions there. But this is the interesting table here. Suppose we try to achieve Kyoto targets, right, in the United States, and we have not signed on to the treaty. But suppose we did, and we were trying to achieve a 7% reduction in carbon dioxide emissions relative to 1990 baseline levels. Or even if we had an increase of 1/4 relative to 1990 levels. Here is the expected business as usual production of energy from coal. Right? If we want to achieve a 7% reduction in carbon dioxide releases relative to 1990 levels, then we have to reduce, relative to business as usual, we would have to reduce our coal consumption by almost 100%. We'd have to almost get rid of all our coal-fired power plants. Okay? Imagine that. And you can see why people were resistant to Kyoto. Even if we want a 25% increase relative to 1990 baseline levels, we'd still have to get rid of about 40% of our coal energy relative to business as usual. Naturally, renewable resources would be up what's predicted to be 1,500%. This is it for wind relative to what's expected by 2020. Biomass up by 3,400%. Okay. Natural gas would go up too. Nuclear would go up a lot also. Right? So you see, these are tough targets to hit. And a lot of people who think we should sign on to Kyoto, people I know, haven't looked at these numbers. Right? I mean, these are real problems. We have to do something about this. Radical change. Right? I'm sure a lot of people would sign on to it. Right? But we should be realistic about what it's going to entail. This is a very profound table when you look at it. Okay, P2 101, Pollution Prevention 101 for coal-fired power plants. Right? Reduce coal consumption. It's simple. Turn off the lights. Right? The more energy efficient you are, the less coal you burn. That's obvious. Okay? And there's a lot of things you can do. You can match electric motors to the job. You don't have to oversize motors, but unfortunately, a lot of people leave this university and they don't know how to do that. Better lighting systems, more efficient manufacturing processes. Use of low sulfur coal, of course. Clean coal technology you've heard of. Fact or fiction, I'll leave it up to you to decide. Develop solar, wind, renewable sources. Increasing conversion efficiency and, of course, transmission efficiency. Right? Again, we lose about 2/3 of it delivering our electricity to the customer. Okay. So some pretty obvious things. Micropower is something people are talking about now. In fact, they're considering putting a microturbine generator over at FXB building, just adjacent to us here. Imagine if we ran our own electricity generation systems. For instance, I've got a natural gas supply, and I have my own turbine that provides my own electricity. Right? We know that our grid is relatively unstable. We learned that in August. Right? It's not the most robust system out there. And if it's critical for me to have a good solid energy supply, electricity supply, then I might hook up my own microturbine. Maybe I could sell energy back to the grid. What if I had a good solar collector? What if I had a fuel cell, right, and a source of hydrogen, right? Well, here is basically the economies of scale as a function of price. So over here you see dollars per kilowatt hour, or per kilowatt, I'm sorry. And here's pulverized coal, right? You need really big coal-fired power plants to deliver this energy in a cost-effective way, right? So you can't really do it at the small scale. It's not cost-effective. We can use fuel cells, we can use solar, we can use microturbines at a much smaller scale. And imagine you could go back and sell some electricity back to the grid, right? Maybe using cleaner forms of energy, right? More distributed sources. When we talked about the diffusion of these fuel cell vehicles, right, we talked about hospitals and companies having their own sources of electricity, generating it themselves, right? This actually came from an Economist article from a couple years back, where they were advocating more deregulation, more ad hoc electricity generation, so the whole network might be a bit more stable, right? But there's a lot of barriers to entry, right? We know that the grid is antiquated. You and me to get on it and to make money off of it. Subsidies, of course, to industry in the form of infrastructure and lax enforcement of carbon taxes, and here we don't have any carbon taxes. We've grandfathered a lot of our electricity plants. The real costs of global warming are not found anywhere in the cost of producing electricity. Right? So there are a lot of barriers to this type of a world, but there are even free marketers who think this would be a good idea. Okay, that's pretty much what I want to say about stationary plants before talking about mobile sources. Are there any questions? All right, stuff you probably know. We're just putting it all together and giving you a sense of scale. Question?
We talked a lot about coal fuel burning power plants. What is the
we didn't talk a lot about nuclear.
Right. I dodged that like, like the plague. Yeah, because, you get into a lot of emotion the minute you bring up nuclear. And I think we know what those arguments are. This is clean. I mean, in the sense that of the pollutants we talk to, they all pretty much go away. Right? So what are you left with is 10,000 years of a waste that you need to keep out of the air and out of the water. Right? And do you really want to provide that as an inheritance? Key issue. Another key issue is security, right? How safe are these plants from terrorism, right? And the enrichment of the fuel for these plants that can be used as weapons, right? And there's a lot in the news these days about North Korea and this issue, Iran and this issue, right? Those are key elements, and it gets down to your valuation of risk and security, right, and intergenerational equity. And there's not too much technical we can say about it. I can talk to you about how a nuclear plant works. I took a course in nuclear engineering. I was just curious in undergrad, and we could talk a lot about it. But at the end of the day, you just come back to those issues, right? It's technically robust. We got it down pat. If you run them right, there isn't too much concern of a 3-mile island or a Chernobyl. I mean, that can be avoided. Those were really stupid accidents when you get right down to it. They can be managed. But, there's a lot of emotion that plays into it. Was there another point you were looking for?
I know that, I can't remember exactly what plant it was, but it was originally targeted as a nuclear plant because of, I guess, all the emotion and the costs that surrounded it. It ended up being converted. The plant's converted from a coal burning or a nuclear plant to a coal burning plant.
They take a real long time to build, and of course the neighbors don't like it, but even in the greater area, these plants have been heavily subsidized. They're extra. You think a coal-fired power plant is expensive? Man, look at a nuclear power plant. That is, I don't have a sense of the scale, but the numbers are huge, and the point there is that they have been heavily subsidized in the past. And fluctuations in cost, fluctuations in government expenditures and tax revenue and the economy can affect the construction of a single power plant in its own life, right? So in ramping them up and ramping them down, it takes a long, long time. So yeah, that's a perfectly natural thing to happen. It's happened in the past for sure.
Could you give us a very brief, what elements go into the nuclear reactor and what comes out that makes it so dangerous for the waste, as a waste?
There are different ways to run them. I believe it's uranium-235. That's the primary input. But we don't, rather than talk about the elements, because I could get it wrong. It's been a long time, about 10 years since I took that course. But I can bring a graph in at some point. But the key is that you're taking a fuel, uranium, and you're allowing it to undergo a set of chain reactions which are controlled. Okay, so basically there's some neutrons involved and some bombardment along the way. And you take one radioactive material and you produce another via a set of chain reactions. And in the process, you're creating heat, which then can, of course, make steam and run a turbine. Actually, I had a graph, and I pulled it out. I probably should put it back in. So Wednesday, I'll give you that one, okay, about how that chain reaction actually works. I don't want to speak incorrectly, so I'll just stay at the real high level. But it's mostly uranium, and that uranium can be enriched to make weapons. Right, so that's the other. In the form of the enrichment is the difference between an ordinary nuclear waste from a power plant and weapons grade. It could be plutonium, actually. Generally, it's better for the weapons. Right, you can use plutonium also. So I'll just give you a couple slides on that on Wednesday, right? Because it is good to know how the technology works, right, and where that comes from. But it's 80-20 here in Michigan. I think my memory is coming back to me now in terms of the distribution, coal versus nuclear.
So the plutonium is not good for Used just as a fuel in the plant?
I'll come back to it. I have some numbers on this, so I can give you an accurate answer on Wednesday.
You haven't mentioned like thermal pollution. Is that just kind of irrelevant to the whole overall impact of the environment?
Thermal pollution is important, actually. It's more important in water than, because if you had one of these plants downtown, it'd be a real nightmare. But they're not, so most of it relates to the ejection of the cooling water into a natural lake, for instance. And it's a real problem in that you don't want to take energy to cool that water down, right? So they just kind of let it happen. And if you create a receiving water, then of course that receiving water can have its own impact on what should have been there in the first place. If it's a natural water, what that heat does is it really has two effects. One is it decreases the amount of oxygen that the water can hold. Okay, so the same dissolved oxygen deficit, like you looked at in the homework, will have a bigger impact because that saturated level goes down. Also, plants and animals use that oxygen at a higher rate. Metabolic rates go up, right? So they need more oxygen, and there's less of it. So it does have a major impact on the ecology of the receiving waters, for sure. Do microorganisms grow faster in warm water? Yeah, of course. So they'll actually do better. They talk about eutrophication and formation of layers on top of, like scum layers on top of the water and things like that. They'll be more likely to happen.
So is there a correlation between like red tides and stuff like that with just the human?
Not.
No, or just that's natural occurring phenomenon?
There's so much debate about red tides that it is natural, but people believe that it is exacerbated by runoff of agricultural fertilizers, right? But the link is really hard to establish. So you're talking down in Florida, right? They had this incident that, I don't remember what year it was, a few years back, where it was really bad, right? And they were trying to pin it down on agriculture. And the last I heard of that story, it was a tough connection to make. People believe it, but they don't really know. But it's not necessarily the thermal pollution, although that would contribute to it, right? Because if you have a red tide environment, now you're allowing the microorganisms to grow more easily. Yeah, it would. But I think this link is probably a step removed even from some of the hypotheses that are out there. That's another good one. Excellent, excellent. So I'll come in a little bit on Wednesday with some nuclear. I'll look up the red tide issue, see if anything's happened. Since that incident, I haven't heard anything. Probably somebody's figured out what happened, or hopefully they have. What's petroleum? Question to you.
Oil. It comes out of the
It's
ground.
used to make oil?
Well, it's a natural resource out of the ground that is used to make oil primarily, I imagine.
Okay, well that's what we use it most for. But is there anything else we use petroleum for?
Food.
Anything else about it for?
Food? Yeah, sure.
Vaseline?
Vaseline? Plastic? Right? Gases? Methane, propane? The thing to know about petroleum is that it's not just C7H14. That's pretty much what you're pumping out of the gas tank. There's a very large distribution, a wide distribution of hydrocarbons that come out with petroleum. Some are gases. Some are very heavy waxes, gunky-like stuff. You can get hydrocarbon chains going up to C70, right? So here's methane's a single carbon, ethane, double carbon. Right? Cyclopentane here, cyclopropane. Some of these constituents in the petroleum might have bound nitrogen. So if you combust it and it has bound nitrogen, you've got fuel NOx. There's thermal NOx and fuel NOx. We'll come to Wednesday. Okay. They can also contain sulfur compounds. So when I refine the petroleum to make gasoline, then there's some sulfur production. Right? We talked about that earlier. Okay, but it's a wide distribution of materials. Nitrogen oxides, the most important ones are nitric oxide, NO, and nitrogen dioxide, NO2. Okay? And mobile sources are roughly half of the NOx that's produced. And we talked about direct health hazards from NOx as a contributor to photochemical smog, right? Ground level ozone. And there are two sources. One is fuel NOx, as I just mentioned. But I want to just conclude here by talking about thermal NOx. Okay? If you've got nitrogen in the fuel and you burn it, you can produce nitric oxide, nitrogen dioxide. That's probably expected because you have temperature and you have oxygen, so I get NOx. Now, thermal NOx comes from the air, right? Combustion involves air, and on Wednesday I'll give you the equation for combustion. And we'll talk a little bit about fuel-rich and fuel-lean combustion. But basically we're talking about the thermal fusion of nitrogen and oxygen to form nitric oxide and nitrogen dioxide. Here it is. Basically, you've got molecular nitrogen. That's found in the air. About I don't know, 70% or 75% of the air is nitrogen. Also have a lot of oxygen in the air, molecular oxygen. So what happens is you've got your first reaction here. This is would happen inside of an engine. So you've got monatomic oxygen combining with molecular nitrogen to produce nitric oxide, plus an extra N, which can now cascade down, react with molecular oxygen, forming nitric oxide and a single O. So you've got basically a balanced set of reactions here that describe the combination of molecular nitrogen and molecular oxygen to form nitric oxide. And this is the pathway to get nitrogen dioxide. So now that has its own equilibrium equation, but the nitric oxide now can combine with some more oxygen to form nitrogen dioxide. Right, so a cascading set of reactions. And of course, this reaction would have its own equilibrium description. Okay, now I'm just going to take you back here for you to think about for Wednesday. Here is, you probably remember doing problems on equilibrium rate reactions. When I've got an equation such as this, N2 plus O2 becomes 2NO. The equilibrium rate coefficient, the K, describes how likely this reaction is to occur. Has this reaction shifted to the right, or is this reaction more likely to stay to the left? That's described by a single parameter, the equilibrium coefficient. And you'll also remember that that was a function of temperature. Okay, so you basically take, and I've written concentration here as partial pressure because we're talking about gases. So if I've got 20% oxygen in the atmosphere, then the partial pressure of oxygen is 0.2. Okay. So basically here, if you stretch your memories to remember, but it's reactants over products. So you've got the reaction here in the numerator, and I'm sorry, the products over the reactants. Here's the product, nitric oxide. Here's the reactant, molecular nitrogen, the reactant, molecular oxygen. And you get the square here because you've got 2 moles being created, right? Everybody's seen this before. Right? And here's the equilibrium rate coefficient. And we have an equilibrium rate coefficient likewise for the production of nitrogen dioxide. Okay? And here's getting to the upshot. We'll go through a problem on Wednesday. But you see here, as the temperature goes up, nitric oxide is much, much more likely to occur. That reaction shifting to the right. If I show you here, if this number is real big, K is really big, right? So if K is growing by 26 orders of magnitude when you go from room temperature to combustion temperatures, right? So nitric oxide happens at temperature, thermal fusion of nitrogen, molecular nitrogen, and molecular oxygen. Okay, and of course, nitrogen dioxide goes down, but it doesn't go down nearly as much. So the net is that you get NOx at higher temperatures. And we'll go through a problem which demonstrates this on Wednesday. Okay, we'll talk a little bit more about fuel consumption. I promised a slide on nuclear. And hopefully in the meantime, you'll have a really nice fall study break. Okay, and a nice weekend too. All right, we'll see you when. We need to finish up talking about combustion. We're talking about the production of NOx pollution last time. We talked about thermal NOx that's formed under temperature in a combustion reactor. I could talk about the inside of a cylinder head, right? But we've got here the basic equations talking about the thermal fusion of nitrogen and oxygen to form nitric oxide. And we reminded ourselves what these, the form of these equilibrium equations take on here. And I'm trying to get the pointer. There we go. On the left-hand side, we've got molecular nitrogen, molecular oxygen forming nitric oxide. We can establish a equilibrium equation with our equilibrium coefficient K that is basically the partial pressure of the reactants, the partial pressure of the products over the reactants. Okay, so we remember because there's 2 nitric oxide, that ends up being a square term. Okay, P is a partial pressure in atmospheres. Nitric oxide, in turn, can create nitrogen dioxide, another component of NOx, and this has its own equilibrium equation. And here we've got the partial pressure of nitrogen dioxide over the partial pressure of nitric oxide times the partial pressure of molecular oxygen to the 1/2, because this is really monatomic oxygen. Okay. We reviewed the temperatures at which these reactions occur, and what we learned was that the nitric oxide equilibrium coefficient here, 26 orders of magnitude difference as we go from room temperature to combustion temperatures. Okay, so the nitric oxide is more likely to form. That reaction shifts to the right when the temperatures go up. The reaction shifts to the left for nitrogen dioxide, but not nearly as much. So we can expect that the NOx formation, as you know, will increase with temperature. So if we look at an example calculating the thermal NOx concentration at a 2,000 Kelvin flue gas temperature, that would be in the exhaust pipe. And we give the flue gas composition here, 76% molecular nitrogen, 4% molecular oxygen, 8% carbon dioxide, and 12% water. Why so much carbon dioxide? Of course, this is the reactants, the products of a combustion reaction, far higher concentration of carbon dioxide. The carbon, the C7H14 gasoline becomes, the carbon in the gasoline becomes carbon dioxide. Okay, so how would we calculate the NOx concentration and the ratio of nitric oxide to nitrogen dioxide? Well, we take our equilibrium equation here that we just went over, and we substitute what we know. We're given in the previous table the equilibrium coefficient for nitric oxide. We know the partial pressure of nitrogen is given to us, and the partial pressure of molecular oxygen is given to us. So we can go back and solve for the partial pressure of nitric oxide. And that would be 3.49 times 10 to the minus 6, or 3,490 parts per million. Okay, so just substituting directly in. We know that we need the nitric oxide partial pressure to calculate the partial pressure of nitrogen dioxide. So we substitute basically 3.49 times 10 to the minus 6 in. That's from part A here. We have the partial pressure of oxygen, again, given to us as 4% or 0.04. And we go back to our table for the equilibrium coefficient at 2,000 Kelvin. Okay, and here is a typo. I know it's not 4 times 10 to the minus 4. That's a cut and paste error for sure. Let's go back and see what that number should be. It should be 3.5 times 10 to the minus 3. Oh, no, it doesn't round up. I thought maybe it was a rounding thing, but no, it's just a cut and paste error. Okay, so it's 3.5 times 10 to the minus 3. And we get 2.4 parts per million. I'm pretty sure that that number is correct. Okay, so you just substitute into the equations. And we've got about 3,500 parts per million, about 2 parts per million, and the NOx concentration is therefore about 3,500 parts per million, and the ratio of NO to NO2 is about 1,500. Okay, so more nitric oxide production. Why is that important? Why might we care which form that the NOx is in, nitric oxide versus nitrogen dioxide? That's a question that we'll answer in about 2 weeks when we talk about smog and ozone. We'll go through some of the reactions involved with the production of photochemical smog. So the answer will wait later, but of course in that session I'll refer back to this one and say, remember about nitric oxide versus nitrogen dioxide. Okay, but you know how to calculate it. Of course, if we were to go through that same procedure at room temperature, roughly, we would see that the NOx concentration is in the parts per trillion range, and we're not very much concerned about it. Okay? Two types of NOx. Fuel NOx, that comes from nitrogen bound up in the fuel that we burn, and thermal NOx, which is the major source, and of course that's going to require more temperature. Okay? And I think that's pretty much all we need to say about it. One point here, we can also use this ratio of nitric oxide to nitrogen dioxide to measure the temperature of the reaction, right? Because it's dependent on temperature, both equilibrium coefficients. And it's not a very tough thing to measure spectrometrically. In fact, you can make small sensors to do that. It's not very common, but you could have this integrated directly into a control system for a powertrain. Nitric acid rain is important. Usually people think about sulfur acid rain, sulfuric acid, as a principal cause of acid rain. It's not the only cause. In fact, if we look at mid-1990 levels, nitric acid contributions to acid rain, in Germany anyway, were on par with sulfur acid contributions to acid rain. Okay, that's basically what this chart's showing. Roughly, same order of magnitude here for sulfur dioxide and nitrogen oxides. Okay. Any questions about those types of calculations before we move forward? Okay, John?
You mentioned Germany a lot. Do these not exist? Same kind of measurements exist in the U.S.?
I haven't seen numbers. I wouldn't be surprised if they were the same, but you can't really homogenize the United States in the same way you can Germany. Right? It's a lot more, in terms of population density, it's a lot higher there. It's very easy in the United States to find places that aren't very close to roads, that aren't very close to smokestacks and electric power plants. So I would hesitate to just say in the United States in general. Certainly there are places in the U.S. Where this condition holds for sure. Other questions? Okay, this is a cycle we've been through before, right? The Otto cycle, 4-step combustion, right? 4-cycle engine here. Got an intake, a compression, a power, and an exhaust stroke. Basically, you've got some valves here. And if we start with the intake stroke, with the piston moving downward, we've got fuel coming in, right? Pulling that fuel in, then being compressed, heated up. Right? We know from the ideal gas law, PV equals nRT, that gas is going to heat up under the pressure, which is great because we're going to burn it using a spark plug. That's going to provide the power that drives this cycle and the next one. And of course, you've got now spent fuel that needs to be exhausted here, and therefore the exhaust valve opens. Okay. Keeping that in mind, what are the basic pollutants that come out of this process? CO2 is one. What else are we concerned about?
Get some carbon monoxide.
Carbon monoxide? So was there another one in there?
Heat.
Heat, yeah. I haven't heard much about the thermal contribution of vehicles to local climate change in cities. It'd be an interesting thing to better understand. We know concrete has a lot to do, because cities do create their own weather, and cities are generally warmer. But my understanding is they have a lot more to do with the concrete. Does it have anything to do with vehicles? Good question. I don't know. But certainly there is thermal release here.
Nitrogen?
Yeah, nitrogen oxides, and there's two others.
Particulates?
Particulates, and we can say hydrocarbons also.
And metals?
Say again?
Like metals?
Yeah, there can be trace metals in the effluent too. Absolutely. That's a good point. Especially lead, right? Leaded gasoline. Okay, so what we're talking about here is the combustion process. Here's our representation of gasoline. It's a bit more of a mixture. Saying it's just C7H14 is a bit of an oversimplification, but it'll work for us. Combining with the oxygen in air, air also has nitrogen and argon, so we just put them in the equation here, but you can see they're not reacting per se, although we know now some of the nitrogen might react, but just a very small fraction. relative to the amount of nitrogen that's there. So we have something called the oxidation step. Right? So you run the engine a little bit rich and allow that extra fuel that leaks through the engine to burn in the afterburner. And that means there'll be very little carbon monoxide and hydrocarbon left. And because you originally run the engine rich, there'll be relatively less NOx also. Right? The problem with the approach is you are running rich, so you're wasting gasoline. Right? So the fuel efficiency now goes down. So of course, that leads to a little bit higher emissions too. Okay. Another way to reduce emissions is to basically put an EGR reactor here. This is exhaust gas recirculation. So take the exhaust gas and put some of it back into the engine. What that will do is cool down the reaction chamber, which will lead to less NOx formation, right? And of course, it will affect your performance a little bit too, because the oxygen concentration is going to be lower, the CO2 concentration is going to be a little bit higher. So your power is going to go down a little bit if you follow an EGR scheme. Another way to, there we go. Wow, that just zipped in there. That was pretty cool. Anyway, this is a three-way catalytic converter. This is probably an idea you're familiar with. Basically taking some platinum catalysts and putting some stages in the exhaust where basically you've got inside, they call it a three-way catalytic converter because basically three things going on here. One is a reduction catalyst. That's a combination of platinum and rhodium. And what it does is basically reduces the NOx, forming molecular nitrogen. Basically binds up NOx and rips off the oxygen, forming molecular nitrogen, okay, instead of NOx. And then after that, there's another platinum catalyst that encourages oxidation, which oxidizes the carbon monoxide and the hydrocarbons. Right? So it basically works on all three, NOx, hydrocarbons, and carbon monoxide. So that's a great thing. The only difficulty with it is it works in a very narrow range. You have to tailor the catalytic converter to work, both in terms of air-to-fuel ratio, as you can see here. Here's the window where it works, but also in terms of temperature. Right? You know that cold starts lead to higher emissions. Right? That catalytic converter has to warm up to do its duty. Right? So a lot of short trips will lead to higher emissions. Question?
Why does a converter have to be platinum?
You'll have to ask the chemistry gods. I don't know. But it has to do with the binding of, I know for the reduction catalyst for sure, you got to bind that NOx. And it's intuitive that some metals are going to work better than others. And do you need to use metals? I don't know. That's certainly way beyond any knowledge that I have. But it does make sense that certain metals are going to work better than others. And it probably stands to reason that they wouldn't be using platinum if they didn't have to, because it's expensive stuff. Yeah, sure. And it tends to be used a lot in catalytic reactions. A good question. I'll ask some of my chemistry friends to see if I can answer that. But that's simple answers. I don't know. Other questions? Okay. Well, I think that's the third step here is the control system. Basic idea here is monitoring the amount of oxygen leaving in the exhaust and controlling the air-to-fuel ratio. So this system can work, right? We mentioned the air-to-fuel ratio is important, so you want to know if you're lean or you're rich. And so there's basically some sensors actuating the air-to-fuel ratio on the other side of the engine. Okay. Diesel, might be familiar with. Basic idea here is no spark plugs. It doesn't do too great in cold weather. The mixtures here are very lean, and the compression ratios are very high. So what that means is the NOx releases from diesel are going to be of concern, and they are of concern. The fuel is also a little bit different. The emissions tend to be more sooty. Right? They have the higher concentration of soot. In fact, the exhaust from diesel engines has been characterized as probable human carcinogen. Okay, so there are health concerns associated with the use of diesel. but they're much more fuel efficient. Much more fuel efficient. 50 miles per gallon is not uncommon for a diesel engine. I think Volkswagen right now is working on a diesel hybrid engine. I'll be curious to see what the fuel efficiency of that combination will be. You take a standard gasoline engine, you can get about 60 miles per gallon out in a hybrid setup. All right, so take a diesel. I'd be very curious to see what the result of that's going to be. But diesel certainly hasn't taken off in the United States. Because of the health concerns, most of our legislation is more, and we talked about this in the first and second sessions here in the United States, much more focused on human health and safety as a much higher priority than just environmental and ecology concerns. Right? So, diesel has been basically kind of has a bad name. It's beginning to come back here in the U.S. But we haven't had much of a interest in higher gas mileage either, because gas is relatively cheap. You see a lot more diesel vehicles in Europe than in the United States. Okay. I'm going to say a few words about nuclear power because I promised. And I didn't want to speak incorrectly. We talked about some of the issues associated with nuclear power. And when I went back to my notes, and I think I might have mentioned taking a nuclear engineering class back in undergraduate. Basically, the issues we talked about, security, the lifetime of radioactive waste, right? These are the issues. I mean, you can go through the nuclear chemistry, if you will, and how a reactor is set up, and at the end of the day, you're left wondering, the same questions. You basically leave the class with the questions you came in. What are we going to do about security? What are we going to do about the issues of safety? Right? And how does a nuclear power reactor work, and why the interest in nuclear power to begin with? Well, there's a fundamental difference between nuclear power and combustion, in that in combustion what you're doing is breaking bonds, and as the atoms recombine, you've got exothermic reactions, right? Energy produced, right? Big bang, if you will, in combustion. It's different with nuclear power. You're splitting the atom here. And the energy density is a lot higher. We talk about splitting forces of holding protons and neutrons together. Up here, about 80,000 times more energy per kilogram in nuclear fuel than in conventional fossil fuel. Okay, so it's a much higher density. Now, to get that fuel isn't easy. And I guess we should be glad that it isn't too easy to get. Uranium oxides found in certain ores in certain places in certain parts of the world. And a high concentration ore may only be 0.25%. Okay, that's even less than copper that we talked about last time. Moreover, I shouldn't say last time, we talked about refining and smelting. Moreover, the particular isotope of uranium that you need is only 0.7% of natural uranium oxide that you would find. Okay, so you're taking 0.7% of 0.25%. So it takes a lot of effort to mine the uranium oxide, purify it, and then concentrate it to get enough of the isotope you want. Okay, why do you want this particular, what's an isotope? Anybody remember?
It's how many negatives it has on it.
Neutrons.
Neutrons? Okay.
Yeah, it's basically an atom that you've got, normally you have the same number of protons and neutrons, but certain isotopes may have more or less neutrons, right? So we say it's different isotope, but the element is driven by the number of protons. Okay. So uranium-235 basically is a special isotope in that it will absorb neutrons that are called slow-moving. Okay, if they're not slow-moving, it'll just kind of break it up. And that's a very important characteristic, the fact that this isotope will absorb neutrons. It will, and it's shown down here, basically, you see the combination of a neutron and the 235 isotope, making uranium-236. And it is the uranium-236 that is fissile. Okay, talk about splitting the atom. Okay, splitting the element in this case. into barium and krypton. Okay, this is very fissile. Right? It's unstable. And as it breaks down or decays, it will form other elements and release a lot of energy. Okay, we call that gamma radiation, photons. We can collect that and then make steam and turn turbines. Okay, and there are many different reactions, like uranium-236 can break down into xenon and strontium also. Right? And that's not really the point. The point is that, and probably in your chemistry class, you never thought that you could turn one element into another element, right? At least if you took the chemistry class that I did. And you know, it's interesting to think about. But a lot of energy released in the process. And it's a chain reaction. That's a critical point here, that this decay reaction releases more neutrons than you started with. Bring in one, end up with two. So therefore, that reaction can continue. All right, and now you've got more neutrons to be captured by more uranium-235 that's in the fuel, et cetera, et cetera. Okay. And most of that nuclear engineering class that I reviewed was about how you control that chain reaction. Right? What are the rates that the chain proceeds? How do you keep control of the reaction? Okay. This is just a picture showing the neutron being absorbed, slow neutron, 235, making the unstable 236, and you got two neutrons coming out and some fragments here. Okay, so how do you make these neutrons be slow? I've got moderator materials here. If I remember right, it was water was a typical moderator material. Slows down the neutrons, slows down the chain reactions. And you don't make all the nuclear fuel fissile. Only about 3 to 4% of it is fissile, right? And of course, that's a critical parameter. How much of the fuel is fissile? So you've got a sort of steady state power generation. Okay. In terms of the environment, right? This is great. You didn't see CO2 anywhere, right? And if you're not concerned about the radioactive waste that's created, and if you're not worried about the potential production of nuclear weapons, then this is fantastic, right? Basically, though, the fission products of 235 can decay into these radioactive elements. We mentioned plutonium last time, right? And that can be used to make weapons. So that's one of the fission products of this chain reaction, is plutonium. Also, 235 can release radiation in and of itself. So here's one of our reaction products, xenon, can become cesium, releasing beta particle radiation. Right? This is radioactive emissions, essentially. Alpha particles are protons and neutrons. Beta particles are free electrons. Gamma radiation is photons, like we're familiar with. Right? And none of it's really very good for you. Right? And the extent to which it's not good for you depends on the dose and the type of radiation, whether it's alpha, beta, or gamma radiation. Okay? Also, the uranium-238, which is the most common form of uranium, can also release in this environment alpha radiation. And there is radioactive waste in every step of the way. If we talk about mining, concentration, and if we call this the use phase, and the end of life, every step has radioactive waste associated with it. But by far, the highest concentration of radioactive waste is at the end of life, in these sort of unstable reaction products that you've made. Right? So that's why we're concerned about the radioactive waste. Half-lives of 10,000 associated with these wastes. Okay? That's basically what it says here. And nuclear power, since the 3 Mile Island incident in the late 70s, 79 I think, has really been on its waning stage here in the United States. There haven't been any new nuclear power plants in the United States since that time. There are about 100 still in operation. 60 nuclear projects were canceled since 1980. Okay? And a number of European countries are on the same trajectory, sort of phasing out the use of this technology. In Asia, we've heard in the news these days, a growing number of countries are aggressively developing the technology, okay, for for reasons that some people have been skeptical of. But there, back in the 50s, when nuclear energy was really taking off in terms of our understanding of it, nuclear power plants, et cetera, there was a promise of energy too cheap to meter. Right? There was a lot of promise associated with it. It turns out the cost to produce a new nuclear power plant in the range of $3 to $6 billion. Just recently, there was a nuclear power plant commissioned in China. This is going to take about 15 years to build, and the price tag was about $6 billion. Right, so it's really not too much cheap about it. In life cycle, people wonder if this is really a cost-effective way to go anyway. Okay. So a few words about nuclear. It's going to take us to the end of electricity and power generation. Are there any questions before we talk about atmospheric transport?
What's the main element in radioactive waste?
It's a hodgepodge of things that decay over time. Right? Some of the reactant products at time 0, right? Thallium, cesium, xenon, but these plutonium, right? The waste aspect, it was really curious that I went back to my notes, and I remember my instructor talking just a very small amount about how you make weapons and what's in waste. I remember the day he talked about that. It's like, everybody put your pencil down. I'm just going to tell you a few things, right? Some ethical questions involved. But the book I have a whole nuclear engineering book. It doesn't talk about the distribution of wastes that are produced, just the basic equations that I have here. But the relative percentages, as the type of question you're asking, weren't in there. It was a whole nuclear engineering text. I thought that was a really curious statement to see a book written in the early 90s not talking about waste to any great degree, right, or even waste management. Yeah. I won't name the book, but anyway, I haven't looked more recently if there have been books published. But it's a good question. I don't have the answer. Probably find it on the internet, right? Other questions?